Okay, now let's take a look at the second derivative. So when we're looking at the second derivative, okay, what we want to do is we want to set that equal to 0. So in the numerator, it's a constant, so we need to look at the restrictions in the denominator. Okay, so what do we know? We know that we have x to the 4/3, which is equal to 0, or 6 minus x to the 5/3, which is equal to 0. So x is going to equal 0 here, and over here this becomes 6 minus x, which is equal to 0, and therefore x is going to equal 6. So now what we want to do is we want to use the second derivative test to evaluate f prime at those critical, the second derivative at those critical numbers. Remember that the second derivative test is going to tell us that if f prime of c is equal to 0, then the second derivative is greater than 0, then f has a local minimum and a local maximum at c. So if we take a look here, right, we already know that we have a critical number at 4, 0, and 6. So we want to find f prime of 0, or f double prime of 0, f double prime of 4, and f double prime of 6. So let's go ahead and put our table in here so we can eliminate those and create a new table. So here, this is going to be -8, and then we're going to divide that by x1 to the power of 4/3 times 6 minus x1 to the power of 5/3. Okay, so what happens when we get 0? So if we plug in 0, it's undefined. So we already know it's going to be undefined. Okay, if we plug in 4, we get -0.4. And what happens when we plug in 6? We also know that's going to be undefined. And so with this, we know that f prime of 4, okay, is equal to 0. And we saw that f double prime of 4 is going to be less than 0. So that tells us here that the second derivative test tells us that if we have f prime of 4 is equal to 0 and f double prime is less than 0, then that tells us that we have a local maximum, which is what we got over here. So that just confirmed that we have a local maximum. Okay. So now the next thing we want to do is we want to then now be able to determine whether it's concave up or concave down using the critical numbers that we have for the second derivative of 0 and 6. So let's go ahead and do that. So what we want to do is we draw a number line. We know that we have a critical number or an inflection point possibly at 0 and a possible inflection point at 6. This is going from -infinity to +infinity. So here we have 3 regions. Region 1, region 2, and then region 3. Okay, so for region 1, we can pick x to be -1. Region 2, we can pick x to be +1. And then region 3, we can pick x to be 7. So let's go ahead and plug these numbers into our table. Okay, so this is our second derivative. If we put in -1, then we get a negative result. So we know it's negative here. Okay, if we put in positive 1, then we also get a negative result. And if we put in 7, then we get a positive value. So if we take a look at region 1, we know that since it's negative, that the second derivative is going to be less than 0. And if it's less than 0 on that interval, then it's going to be concave down. Okay, in the second region, we know that it's negative, so that means it's also less than 0, which means it's concave down. And a third derivative, we can see that the second derivative gave us a positive result, so therefore it's greater than 0, so therefore it's concave up. So now we need to determine if there is an inflection point, or points. Okay, well, in region 1 and 2, it's concave down and concave down. So if it's concave down and concave down, then 0 is not going to be an inflection point. But here we can see that in region 2, it's concave down, and then it goes to concave up at 6. So therefore, 6 is an inflection point. So if 6 is an inflection point, then we want to find f of 6. So let's evaluate that into our function. So here we have the function. Okay, if we put in 6, then we get 0. So therefore, the inflection point is going to be at 6, 0. And so now let's go ahead and graph this on Desmos to confirm our results. So we know that the function is x to the 2/3 times 6 minus x to the 1/3. Okay, so you can see some of our points here. So we have a local maximum at 4, 3.17. We have a local minimum at 0, 0. Okay, and let's go ahead and look a little further here. Okay, so there's 0, 0. And then we also have a inflection point at 6, 0. So if we change our viewing rectangle from -2 to 8 from our x-axis and the y-axis from -7 to 5, we can see this a little bit better here. Again, we can see that we have a local minimum at 0, 0. We can see that we have a local maximum here. And then there is our inflection point. So let me go ahead and copy this. So we can confirm our graphing results. Okay, so again, there is our maximum, our local max. So let me go ahead and highlight that here. So we have our local max at 4, 3.175. We have our local minimum at 0, 0. And then we can also see that we have our inflection point at 6, 0. And then notice that in the first region, it goes from -infinity to 0, it's concave down. So from -infinity to 0, it's concave down. And then it's also concave down from 0 to 6. So there it's concave down there. And then from 6 to +infinity, we can see now it turns concave up. And that concludes this problem.